Two galaxies are falling toward each other right now, somewhere in the dark beyond anything a name could reach. They have been falling for longer than the Earth has existed, and they will still be falling, still turning slowly inward, long after everything alive on this world has come and gone and been forgotten by the universe that made it. The fall takes time on a scale that the body cannot feel. From the first moment of gravitational contact to the final slow settling into one, a galaxy merger unfolds across somewhere between 1 billion and 3 billion years, depending on how the two systems first approached, how fast they were moving, and at what angle their paths crossed. 1 billion years is not a number that lands cleanly in the mind. Place it against something the body knows. If every year of Earth's entire history were compressed into a single day, 1 billion years would be roughly 6 of those days. A galaxy merger, start to finish, takes somewhere between 6 and 18 of them, quiet days, days in which nothing on any human timescale would appear to change at all. And yet, at the end of all those days, two vast spiraling systems of stars and gas and ancient dark matter would have become one. This is the architecture of the slowest kind of event in the known universe. Not slow because nothing is happening. Slow because what is happening is enormous. Each of these galaxies carries within it 100 billion stars, or something near that number. The stars are not packed tightly, not touching, not even close to touching. Between each star and its nearest neighbor, the distances are so vast that if the sun were the size of an orange, its nearest stellar companion would be another orange, sitting somewhere in another country. A galaxy is mostly empty space, ornamented by light, and yet two galaxies, falling into each other across these immense internal distances, still manage to reshape one another completely. They do it without a single star making contact with another star. They do it through gravity alone. Before the luminous disks of two merging galaxies come anywhere near each other, something else has already begun. Each galaxy sits embedded within an invisible structure far larger than anything the eye could detect, a dark matter halo. It extends outward from the visible galaxy in every direction, hundreds of thousands of light years beyond the last faint star, a diffuse and structureless sphere of something that neither emits light nor absorbs it, detectable only through its gravitational influence on the matter around it. The halo dwarfs the galaxy. It surrounds the way a vast atmosphere might dwarf the thin crust of a small planet. If the Milky Way's luminous disk, roughly 100,000 light-years across, were a coin held at arm's length, the dark matter halo surrounding it would be a sphere the size of a room. All of that invisible mass, all of that gravitational reach, extends outward into the dark where no stars exist. When two galaxies begin to approach one another, their halos make first contact, hundreds of thousands of light years before the visible disks are anywhere near each other. The luminous galaxies, seen from a great enough distance, would look like two bright disks drifting toward each other in open space, unhurried and widely separated, their spiral arms still intact, their cores still bright and undisturbed. And yet already, at that great separation, the halos have begun to pull on one another. Already, the gravitational conversation has started. Already the outcome, in the broadest terms, has been set. Whether two galaxies will truly merge or pass each other and drift apart again comes down to a single question of energy. If the total orbital energy of the system is above zero, the galaxies have enough kinetic energy to escape each other's gravity and separate. If it falls below zero, they are bound. They cannot leave. The passage may be dramatic, the first close approach pulling streamers of stars and gas from each system, reshaping their faces entirely. But after that first pass, the two will slow, turn, and fall back toward each other, and the second approach will bring them closer, and the third closer still, and eventually across many such passages, spread across billions of years, they will settle into one. The mechanism that drives this slow inward spiral has a name that sounds almost paradoxical: dynamical friction. Not the friction of two surfaces pressing against each other, not anything the fingertip could feel. This is a friction that acts between a moving galaxy and the sea of dark matter particles through which it travels. As a galaxy moves through the surrounding dark matter halo, its gravity pulls those particles toward it slightly, creating a small concentration of enhanced dark matter density just behind it in the wake of its motion. That slight concentration pulls backward on the galaxy, gently, continuously, over enormous time. The galaxy loses orbital energy to the dark matter in its surroundings, and that energy does not return. It disperses into the halo, and the galaxy, having lost that energy, falls a little deeper into the shared gravitational well. It spirals inward, not in a straight line, not in a sudden plunge, but in a long gradual arc, lasting hundreds of millions of years, drawn by a force so subtle that it would be imperceptible to any observer watching on any human timescale, yet utterly decisive across the time that galaxies have to spend. The two systems do not announce themselves to one another. There is no signal, no moment of recognition. The dark matter halo of one simply begins to feel the gravity of the other, and the long arithmetic of attraction begins its slow and patient work. The first close passage between two merging galaxies is called the pericentric approach. It is the moment of least distance, the closest the two disks come during their initial encounter, and it is the moment when tidal forces act most powerfully on each galaxy's structure. Material at the near edge of each galaxy is pulled more strongly toward the companion than material at the center, and material at the far edge is pulled less. That differential creates a kind of stretching, a torque applied across the entire body of the galaxy that flings material outward and begins to disrupt the geometry that had held for billions of years. The graceful spiral arms, wound over eons of rotation, begin to be pulled askew. Long trails of stars arc outward into the surrounding space. The shape that took so long to build is suddenly, on cosmic timescales, being rewritten, and then the two disks sweep past one another and separate again. The separation is not a reversal. It is not an escape. If the energy is negative, the two systems are already committed to what comes next. They move apart, but slower than they came together. They slow, stop at some great distance, and then begin again the inward fall. The second approach will be closer, the disruption will be greater, and each subsequent passage will drive the two systems further from anything recognizable as what they were before. From very far away, at some great distance across the universe, the whole encounter might look like a slow dance. Two bright disks approaching, sweeping past, separating, returning, their shapes distorting and recovering and distorting again with each pass, their outer regions gradually bleeding into a shared envelope of scattered stars, their cores still glowing but slowly converging, a dance that takes a billion years to complete a single turn, and patient in a way that nothing alive has ever been able to witness from beginning to end. The classification of mergers into types depends largely on the relative masses of the two galaxies involved. When the two participants are roughly matched in mass, within a factor of about 4 to 1, the merger is called a major merger. These are the events with the most dramatic consequences. A major merger disrupts the spiral structure of both galaxies. It can trigger an intense episode of star formation across the combined system. It rearranges the distribution of stars and gas more completely than any other single process in a galaxy's life. After a major merger, the remnant rarely resembles either of its progenitors. The elegant, rotationally organized disk is gone. What remains tends towards something rounder, smoother, more disordered, a structure shaped not by the orderly rotation that built it, but by the collision that unmade it. When one galaxy is much smaller than the other, the result is a minor merger, and the consequences fall unevenly. The smaller galaxy loses itself in the larger. Its stars are scattered through the larger system's halo, its gas absorbed or stripped away, its distinct identity dissolved over hundreds of millions of years into the ambient population of the larger host. The larger galaxy survives largely intact, its structure disturbed perhaps only in its outer regions, its overall shape preserved. Yet even minor mergers are not without consequence. Material from the smaller galaxy adds to the mass of the larger. The outer halo is enriched. The distribution of stars shifts. Over the course of cosmic history, most large galaxies have experienced many such encounters, absorbing smaller companions gradually, growing not through one dramatic event, but through many quiet accretions spread across billions of years. Both kinds of mergers have shaped the galaxies visible in the present-day universe. The great elliptical galaxies that sit at the centers of clusters, vast and nearly featureless, their stars moving in every direction without the ordered rotation of a disk. Those are widely understood to be the products of many mergers over long time, the accumulated residue of multiple major collisions in which the ordered structure of spirals was undone, and something older and smoother took its place. And the spiral galaxies themselves, those still intact, those that have not yet found a companion massive enough to disrupt them, carry in their outer halos the faint dispersed remains of all the smaller systems they have consumed over their long histories. There was a time when the universe was much younger and much denser, and galaxy collisions were far more frequent than they are today. In the period roughly 2 to 10 billion years after the Big Bang, when the universe had not yet expanded to the vast, thinly distributed structure it presents now, galaxies were packed more closely together, their separations smaller, their orbital velocities more likely to carry them into each other's gravitational reach. Observations of the distant universe, looking back across billions of light years to see galaxies as they were in that earlier time, reveal a much higher rate of disturbed morphologies, close pairs, and interacting systems, and the number of ongoing mergers per unit volume of space was several times higher at redshifts around 1 or 2 than it is in the present epoch. Some estimates place the merger rate at redshifts between 1 and 3 at several times the current rate, with the exact ratio depending on the mass range examined. This was the peak era of galactic collision. The universe, young and still contracting in its densest regions, was building structure rapidly through the merging of smaller things into larger ones. Dark matter halos fell together. The gas within them collapsed and formed stars. The galaxies that emerged from those early epochs were smaller, more irregular, more numerous, and more likely to find a companion and collide with it. The great elliptical galaxies now seen at the hearts of clusters grew, in large part during this period of intense merger activity, built up through repeated collisions in dense environments where the probability of encounter was high. The universe has since spread out. Cosmic expansion has pulled the average distances between galaxies wider, reducing the rate at which new encounters begin. The population of close pairs has declined. The fraction of galaxies showing the strongly disturbed morphologies typical of active major mergers has fallen. The era of greatest collision is not happening now. It happened billions of years ago, before the Earth existed, before the Sun had yet condensed from its molecular cloud, before even the oldest rocks on any world had formed. The mergers that built the largest galaxies, that seeded the universe with the chemical products of intense starburst episodes, that created the most luminous objects the universe has ever contained, all of that activity belongs to a younger, denser, more turbulent time that can now only be seen by looking very far away, across space, and therefore very far back in time. What remains now, in the present era of the universe, is a quieter population of interactions. Mergers still happen, the conditions for them still exist. In the dense cores of galaxy clusters, where galaxies are packed closely enough to frequently disturb one another's paths, interactions continue. In the field, where isolated galaxies move more freely through large volumes of space, chance encounters still occur, driven by the same gravitational arithmetic that governed the earlier universe. But the overall rate is lower. The encounters are the late, unhurried events of a cosmos that has spread itself thin and cooled into its current configuration. A galaxy found in a close pair today, two luminous disks separated by only a few 100,000 light years, their outer regions already beginning to distort, their halos already overlapping and beginning the process of dynamical friction. Such a system is in some sense a relic of an earlier cosmic style. It is living out a process that was once commonplace, that once shaped the universe more dramatically than any other force, but that now happens less often, in fewer places, with less of the accompanying activity that the younger gas-rich mergers of the early universe produced. The galaxies falling toward each other now across the present-day sky are falling as their predecessors fell across a far younger and more crowded sky. The physics has not changed. Dark matter halos still begin their gravitational interaction at great separation. Dynamical friction still draws the two nuclei together across hundreds of millions of years. Pericentric passages still fling arcs of stars outward through the surrounding dark. The whole slow choreography proceeds on its same ancient schedule. What has changed is only the frequency and the richness of the gas supply, and the rate at which new encounters begin to replace those that have finished. The deep past holds the full richness of what galaxy mergers can do. The present holds their quieter descendants. And somewhere between the two, spread across the sky in every direction at various stages of their long inward spirals, are the galaxies currently living through the process, some just touching, their outer halos barely in contact. Others past their first pericentric approach, their shapes already badly distorted. Others still in their final slow convergence, two nuclei orbiting each other at diminishing separations within a single disturbed host, circling inward through the last few hundreds of millions of years before the cores join and the distinction between the two galaxies disappears entirely. Each one of those systems is a window into a process that took billions of years to get to the frame, visible now. None of them will complete the journey on any time scale that a living thing could track. They are always, from any single moment's perspective, in the middle of something vast, and the middle is where they will remain for longer than the age of everything on Earth. Two dark matter halos pressed against each other at a great separation, their visible galaxies still far apart, still bright and apparently intact, are already in the grip of something that will not release them. The arithmetic of gravity does not offer second chances once the energy falls below zero. The outcome is determined before the luminous disks have come anywhere near each other, before the tidal forces have had a chance to pull the first arc of stars outward into the surrounding dark. The merger is already underway. The billion years remaining are only the working out of what has already been decided. There is something in that which the body can rest against. Not urgency, not threat, only the deep, patient certainty of gravity doing what it always does, drawing mass toward mass, slowly, across distances that make every human concern feel not small, but simply local. The concern is real, the scale is also real. Both things can be true at once, and neither cancels the other. They simply exist at different distances, and the one at the greater distance has more time. The universe in its present form is quieter at the level of galaxy mergers than it was in its most turbulent youth. The stars still shine in their spirals. The dark matter halos still extend their invisible reach outward into the void beyond the last visible edge of every galaxy. The gravitational conversations between neighboring systems still begin, slowly, at separations that make even the galaxies themselves look small. And somewhere right now, invisible to any single eye, but present in the data of every telescope trained on the deep sky, two vast systems of stars and dark matter are beginning the slow inward fall that will take them 1 billion years to complete, and that will end in a single merged body where two distinct galaxies used to be. That merger was not beginning now, in any meaningful sense. It began long before the first light of it reached any instrument. What is visible now is already old. The closing of the distance between two colliding galaxies, even at speeds of hundreds of kilometers each second, takes so long to produce a visible change in separation that observations taken decades apart at the largest telescopes barely register any shift in the two bright cores' positions. The motion is real, the approach is real. The inward spiral toward eventual coalescence is as certain as any process the universe contains. But it is not a thing that can be watched the way a tide can be watched, or a storm, or even the slow creeping of a glacier across a mountain slope. It is a thing that can only be inferred, reconstructed from the physics that governs it and the simulations that trace its mathematics forward through time. The cosmologists and astronomers who study mergers do not watch them happen, they collect snapshots. They find a galaxy pair at one stage of interaction and another pair at a later stage, and by comparing many such systems across the range of their separations and morphologies, they piece together the arc of the process the way a paleontologist pieces together an extinct animal from bones found at different sites by different people over different decades. The animal existed whole, the bones arrived separately, and from the patient assembly of parts, the whole becomes visible again. In the same way, the full biography of a galaxy merger is assembled from many partial glimpses, each caught at a different moment, each contributing one frame to a film that no one has ever watched from beginning to end, and no one ever will. The merger that takes 2 billion years to complete cannot be witnessed by any living thing. It can only be known, and the knowing, painstaking and indirect, built from physics and simulation and the catalogued images of thousands of interacting galaxy pairs, amounts to a picture that is perhaps more complete than a direct observation would allow, because the physics is the same in every case, because the forces that govern one pair govern all of them, because the universe, at this scale, is reliable in a way that makes its vast, unhurried processes legible to patient minds. The dark matter halo of a galaxy stretches outward from the visible disk in all directions into the surrounding void. Hundreds of kiloparsecs, Each kiloparsec is about 3,260 light years, and the halos reach hundreds of them in every direction, so that the total diameter of the unseen gravitational structure surrounding a large galaxy might be 10 or 20 times the diameter of the visible stellar disk at its center. The galaxy as seen in optical light is only the lit part. The galaxy as a gravitational object is vastly larger, a sphere of dark influence so extended that two galaxies whose luminous disks appear widely separated may already have their halos deeply overlapping, already exchanging mass and momentum, already caught in the process that will, given enough time, bring the bright parts together too. This is the first thing to understand about galaxy mergers. The encounter begins not where the light is, but far beyond it. The visible collision is the late stage, the consequence of a gravitational embrace that began long before the luminous disks were anywhere near one another. By the time two galaxies look disturbed in an image, by the time their spiral arms are bent and their outer stars are streaming into tidal tails, and their surface brightnesses show the asymmetries of an ongoing encounter, the dark matter halos have long since overlapped and begun exchanging orbital energy. The visible disturbance is the announcement of something that already started, and dynamical friction, working its slow way through all those hundreds of millions of years, is what keeps the announcement from being the end. Without it, a galaxy that had passed close to a companion and been gravitationally bent might continue outward, slow, and turn back, but if it retained its orbital energy, it would eventually settle into a long, stable orbit, circling its companion forever at a safe distance, never truly merging. Dynamical friction is what prevents this. It bleeds the energy away. Slowly, pass by pass, it removes the capacity for the two systems to maintain a stable wide orbit and forces them instead onto a tightening spiral that ends only in coalescence. It is not fast. Nothing about this process is fast. But it is inevitable, given enough time and given the right initial conditions, and given a universe old enough and patient enough to let it run its course. The universe is old enough. It is 3 times older than the Earth, older than the oldest star visible in the night sky, old enough that the mergers which shaped the largest galaxies in today's universe began when it was a fraction of its current age and have long since finished, leaving only their remnants in the smooth spherical forms of the great ellipticals. The universe had the time. It used it. And what it built through those billions of years of slow gravitational arithmetic is what we live inside. A single galaxy merger placed against the backdrop of cosmic history is not a disruption. It is not an accident. It is one instance of the dominant process by which galaxies have grown across the age of the universe. The great spiral disk might look like a final form, stable and long-lived, rotating at a few hundred kilometers per second around a glowing core. And in human terms, in any terms that a life or a civilization could encompass, it is stable. But measured against the age of the universe, measured against the timescales on which mergers unfold, even the most serene-looking spiral is at most a temporary arrangement, one configuration in a long history of configurations shaped by gravity, and one that may, given enough time and the right neighbor, be undone and remade into something else entirely. The current merger rate of the universe is low by its own historical standards. The galaxies that are falling together now are fewer, and the conditions of the collisions are different from those of the peak era, when the universe was younger and the galaxies richer in gas and more frequent in their encounters. But the process continues, somewhere in the sky, in every direction, At distances ranging from a few tens of millions of light years to the far edge of what any telescope can reach, galaxies are falling toward each other in their slow, inevitable spirals, working out through billions of years the consequences of orbital energies that tipped below zero at some moment in the past. The era of greatest collision has already passed. It lived and burned and built the universe's largest structures, and then faded as the expansion of space carried the average separation between galaxies wider and wider, reducing the rate of new encounters, leaving the remnants of the old ones to finish their long inward spirals in a universe that had by then moved on to something quieter. What remains now is the long tail of that process, the late encounters, the survivors, the systems still completing what they began in a denser and more turbulent time. The universe does not hurry. It never has. The mergers still unfolding in the present sky are not behind schedule. They are not remnants of something failed or incomplete. They are simply at the point in their long arc that the present moment contains, moving inward slowly, as they have been moving for perhaps a billion years already, and as they will continue to move for perhaps another billion or two, before the last distinction between the two original galaxies dissolves into the smooth, unhurried body of what they will have become. Dark matter halos extend their invisible reach outward into the dark right now in all directions, from every galaxy in the observable universe. The luminous disks glow within them, ordered and bright, unaware in any meaningful sense of the vast invisible architecture surrounding them, and of the slow gravitational pulls beginning to tighten from neighboring halos hundreds of thousands of light years away. The first touch has already happened for some. The long inward fall is already underway, and the universe, in its present quiet phase, holds all of these encounters at once, each at a different stage, each unfolding on its own schedule of billions of years, each invisible in its progress to any single observation, but legible in its entirety to the accumulated physics of how gravity works and how long the universe has given it to work. The age of great collision is over, or something close to over. What persists now, unhurried and certain, are the last long arcs of a process that once shaped the universe more completely than anything else. The galaxies falling together now are falling through a quieter cosmos than the one their predecessors fell through. The sky is thinner. The encounters are rarer, but the physics is unchanged, and the time is still available. And somewhere in the vast dark between the stars of distant galaxies, two invisible halos of ancient dark matter are just beginning to pull at one another, setting in motion something that will still be unfinished a billion years from now, and perhaps 2 billion, before it quietly and completely resolves. During a paracentric passage, that first sweeping close approach, when two galaxies come near enough for their gravity to grip each other deeply, the material on the near side of each galaxy is pulled harder toward the companion than the material at the center, and the material at the far side is pulled harder still toward the center than the companion can reach. This difference, felt across tens of thousands of light years of stars and gas and dust, is not violent in the way that word is usually meant. It is slow, it is immense, and it flings material outward along the direction of the orbit in a long curving arc that can stretch for hundreds of thousands of light years before the stars within it begin to thin and fade. These arcs are called tidal tails, and they are among the most beautiful structures the universe makes from gravity alone. A tidal tail is not an explosion. Nothing is thrown. Instead, the differential pull, stronger on the near side, weaker on the far, imparts a net rotation to the galaxy's material, a torque that peels the outer disk away from the gravitational center and sends it drifting in a slow luminous curve outward into the space between galaxies. The stars within it do not clump, they do not spiral. They spread along the arc like light scattered across still water, their spacing growing gradually wider the farther from the galaxy they travel, their collective glow fading from something bright enough to photograph into something so faint it dissolves at the edge of detection. The tail carries within its curve the orbital geometry of the entire encounter. How steeply the companion approached, how fast it moved, how closely it passed, all of this is written in the angle of the tail, and the length of it, and the way it bends. A tidal tail is in this sense a record. Long after the galaxies have moved apart and the first passage is complete, the tail remains, a slow inscription in stars of what happened and how. Two galaxies in the middle of their first close passage often look from the right distance like a pair of wings flung wide. One tail sweeps out in one direction, the other sweeps out behind, in roughly the opposite direction from the companion's path. The two tails together form a shape that has been compared to the wings of a bird, and in at least one celebrated case, to the antennae of an insect. That case is real. Two galaxies called NGC 4038 and NGC 4039, known together as the antennae galaxies, display two long tidal tails produced during a pericentric passage estimated to have occurred somewhere between 200 and 300 million years ago. From the right angle and from a sufficient distance, which here means tens of millions of light years, the two tails sweep outward from the common glow of the colliding pair in elegant, nearly symmetric curves, each one bending away from the system's center like a limb thrown wide. Between them, the two bright galactic nuclei are still distinct, embedded in a disturbed and overlapping halo of stars, where the outer disks of the two galaxies have already merged into one continuous, turbulent envelope of light. The antennae galaxies are close enough, roughly 45 million light-years away, that telescope images resolve not only the tails, but the texture within them, regions of compressed gas glowing between the two nuclei, clusters of young stars forming in the disturbed material, and at the very tips of the two long tails, concentrations of gas and stars that have grown dense enough to develop a kind of local identity of their own. Those concentrations at the tips of the tails are something particular and worth dwelling in. In most collisions, the tidal tail is a disruption. Material is pulled free of the host galaxy, flung outward, and left to disperse. The stars within the tail continue moving, spreading along the arc, gradually thinning until the tail dissolves into the intergalactic field over hundreds of millions of years. This is the ordinary fate of tidal tail material, slow dispersal into the surrounding space, contributing to the faint stellar halos that surround large galaxies, and to the still fainter stellar streams that thread through galaxy groups and clusters. But near the tips of some tidal tails, something different can happen. The material there, gas, dust, and stars stripped from the outer disk of one of the colliding galaxies, can be dense enough and far enough from the gravitational center of the host that local gravity begins to matter. The gas within the tail tip accumulates, it cools. Under its own weight, it begins, slowly and without announcement, to collapse. What forms in such a collapse is a new object, smaller than the galaxies that produce the tail, but coherent in its own right, gravitationally bound, capable of making new stars from the gas it has gathered. It is called a tidal dwarf galaxy, and it carries within it one of the more interesting consequences of how it came to exist. The outer disks of large spiral galaxies are made of material that has already been through a great deal of chemical processing. The stars formed in those disks over billions of years, burning through hydrogen and helium and producing heavier elements, carbon, oxygen, silicon, iron, which were expelled back into the interstellar gas when the stars aged and died. The gas in the outer disk is therefore enriched. When tidal forces strip this material from the disk and pile it into the tip of a tidal tail, the tidal dwarf galaxy that forms from it inherits this enrichment. It is born already containing the products of billions of years of stellar generation that preceded it. This sets tidal dwarf galaxies apart from the small galaxies that formed early in cosmic history, which assembled from far more pristine material. And it sets them apart in another way as well. Ordinary galaxies of every size from dwarf to giant are embedded in dark matter halos. Dark matter makes up most of the total mass of a galaxy system, extending in a diffuse invisible sphere far beyond the luminous stars and gas. This dark matter halo was already present before the galaxy formed, collapsing first, drawing ordinary matter in after it, providing the gravitational well that made everything else possible. When galaxies merge, their dark matter halos merge too. When minor galaxies are accreted by larger ones, their dark matter is stripped and mixed into the larger halo. Dark matter is everywhere in this picture, enveloping every structure at every scale. But tidal dwarf galaxies form from stripped disk material, not from a pre-existing dark matter concentration. The dark matter in a galactic disk is only a small fraction of the total halo mass, and much of even that fraction may not follow the baryonic gas and stars into the tail. A tidal dwarf galaxy, forming from what is essentially a stripped and collapsed region of enriched outer disk, may contain very little dark matter at all. It is in this sense a genuine exception to the rule that all galaxies sit inside dark matter halos, a small, coherent, star-forming object that gravity assembled from the debris of a larger collision without the scaffolding that normally underlies galaxy formation. This is one way the universe makes new things from old ones. The tidal tail that carries such a forming object outward into space is meanwhile fading. Its stars do not brighten, they spread. Over hundreds of millions of years, the arc of the tail grows longer and thinner, its luminosity dropping below the threshold of easy detection, its structure dissolving as the stars within it follow slightly different paths under the gravity of the host system and the surrounding space. The tail does not vanish exactly, it disperses. Its stars become part of the diffuse stellar population that fills the space around and between galaxies, contributing to vast faint structures that wrap around galactic systems like a dim and scattered record of every disturbance in their past. The Sagittarius dwarf galaxy provides a vivid example of where this process can lead. The Sagittarius dwarf is a small galaxy that has been falling into the Milky Way for a long time. It is not a single encounter system. It has passed through or near the plane of the Milky Way's disk multiple times over billions of years, and each passage has stripped material from it. That material forms a stellar stream. It is not a tail in the way the antennae tails are tails, flung outward in a single dramatic arc during a first close pass. Instead, it is a wrapping. The stars stripped from the Sagittarius dwarf over many orbits have spread along the path of its orbit around the Milky Way, distributing themselves in a great loop that winds nearly all the way around the sky. This stream is not visible to the naked eye. The stars in it are too spread out, their combined surface brightness too low against the background of the Milky Way's own stellar field. Detecting it requires comparing the positions and velocities of individual stars across large swaths of sky, looking for the subtle statistical excess that marks a coherent population moving together against the general flow of Milky Way stars. Only with careful surveys, measuring not just where the stars are, but how fast they move and in what direction, does the stream reveal itself as a continuous structure, looping in a great arc through the galactic halo. The Sagittarius stream wraps around almost the entire sky from the inside. Seen not from outside, but from within the Milky Way, it traces the orbital history of a small galaxy being slowly consumed, its material redistributed across a volume so large that no single image could contain it. The stream is old in places and young in others. Different wraps correspond to different passages, each passage stripping a fresh layer of stars from the Sagittarius dwarf and adding them to the growing loop. The dwarf itself still exists, still a recognizable concentration of stars, but it is being slowly dispersed by each encounter, its outer layers continuously pulled away, its future as a distinct object, limited to however many more passages remain before its coherence is gone entirely. This is what a minor merger looks like, played out over billions of years. Not two equal systems meeting in a dramatic exchange of tidal tails and bridges, but one large system patiently pulling apart a smaller one, orbit by orbit, strip by strip, until the smaller one is gone and its material is woven into the fabric of the larger. The tidal bridge is a related structure and a different one, where a tidal tail forms on the far side of a galaxy from its companion. The material that was pulled away from the companion's reach and flung outward by the differential pull, a tidal bridge forms on the near side. Here, the situation is reversed. The material between the two galaxies, facing the companion, is drawn toward it rather than away from it. Gravity pulls this near-side material in the direction of the companion's center, and as the two galaxies separate after their close pass, a stream of stars and gas is left extending between them, connecting their two luminous bodies across the gap. A tidal bridge is quieter than a tail. It does not sweep outward in a long arc. It hangs in the space between two galaxies like a faint thread, drawn taut between two bright nodes, its own light too dim to see without careful observation. In neutral hydrogen gas, the raw material of star formation, detectable at radio wavelengths, bridges can be traced with instruments like the Very Large Array, which resolves the radio emission from hydrogen clouds into coherent structures that cross from one galaxy to another across distances of tens of thousands of light years. The bridge matters for what it carries. Gas flowing along a tidal bridge from one galaxy toward another can arrive at the companion as a genuine transfer of material. A gas-rich galaxy and a gas-poor one, in close interaction, may, through this mechanism, share some of what they have. The gas-poor system gains new raw material. The enriched outer disk gas from the donor arrives in a new environment. What happens next depends on how much arrives and where, and how the receiving galaxy's own structure responds. But the bridge is the pathway, and in some systems, it is through the bridge that material first crosses the gap between two systems that have not yet truly merged. The antennae galaxies have both. Between their two nuclei, in the overlap region where the outer disks of the two galaxies have already interpenetrated, a tidal bridge of compressed gas glows in radio wavelengths and in other tracers of dense interstellar material. This region, the space between the two nuclei, where gas from both galaxies has collided and been compressed, is one of the most active parts of the entire system. It is where the interaction is most immediately physical, where the two galaxies are not just gravitationally perturbed, but materially overlapping, gas running into gas, pressures rising, and the conditions for something new building rapidly within the overlap. That something is reserved for a different telling. What matters here is the structure. Two long tails, each one encoding the orbital geometry of the encounter in the slow curve of its stars, a bridge of compressed gas hanging between two nuclei that are still distinct but no longer separate. And at the tips of the tails, dense knots of gas and stars that are beginning, quietly and unhurriedly, to assemble themselves into something new. This is what gravity does with galaxies when they pass close enough to grip each other. It does not simply destroy, it reshapes. It strips the outer layers and flings them into space in long luminous arcs. It draws threads of material across the gap between two systems. It compresses and accumulates and concentrates, and in concentrating, it creates conditions where structures that never existed before can form in the debris of what was there before. The tail sweeping outward from a galaxy during a close passage is enormous by any measure the body can hold. The antennae's tidal tails extend well over 100,000 light-years from the central pair. 100,000 light-years is roughly the diameter of the Milky Way's luminous disk. The tails, in other words, are as long as the galaxy itself is wide. They sweep through a volume of space so large that the entire architecture of a major spiral galaxy, its disk, its central bar, its spiral arms, could be placed within the arc of one tail and still not reach from end to end. Across that entire length, individual stars, not clouds of gas so compressed they glow, not the sheets of excited hydrogen that mark regions of active star formation, but individual aging stars from the outer disk, their light faint and golden and old, spread along the tail's curve at the spacing that the differential pull of the encounter has imposed on them. The tail is populated, but not crowded. Its average density is far lower than the interior of either galaxy. The stars within it are separated by light years from their nearest neighbors, as they always were in the outer disk, but now moving slowly along a path that curves away from everything they once orbited. They will move along that path for a very long time, over hundreds of millions of years, as the two parent galaxies complete their second and third passes and begin to coalesce into a single merged system. The tidal tails that marked the first encounter continue to spread and fade. Their stars, no longer strongly bound to the gravitational center of the interaction, follow their own paths through the surrounding space. Some drift outward, slowing gradually as they climb away from the merged system's gravity and eventually reversing, falling back in. Some escape entirely, joining the diffuse intergalactic stellar population that floats between galaxies in groups and clusters. The tail, as a visible structure, dissolves over a timescale of roughly 1 billion years, but the stars it contained do not disappear. They disperse. The dissolved tail becomes the diffuse stellar halo. Large elliptical galaxies, the kinds of objects that result from major mergers between massive spirals, are surrounded by extended halos of old, metal-poor stars. Some of those stars came from the outer disks of the progenitor galaxies, flung into the halo by tidal forces during the merger. Some came from the satellite galaxies that were accreted and disrupted over billions of years of minor mergers. And some came from the tidal dwarf galaxies that formed at the tips of old tidal tails and were themselves later disrupted by the gravity of the growing merged system. The halo is, in this sense, a library. Encoded in the positions and velocities and chemical compositions of its individual stars is the full history of every major and minor interaction the galaxy has undergone across its lifetime. No single record is easy to read. The stars are old and spread through a volume so large that surveying them all requires enormous patience and precise instruments. But with sufficient data, measuring the velocity and chemical abundance of individual stars across millions of light years of halo volume, the streams and overdensities left by past mergers can be recovered. The history can, piece by piece, be reconstructed. The Sagittarius stream is the most clearly visible example of this reconstruction within the Milky Way. But there are fainter structures as well, shells and streams and excess regions in the stellar halo that point to older, more distant, more thoroughly dissolved encounters. Each one is a dissolved tail, a redistributed satellite, a record of gravity's patient work across billions of years of cosmic time. To look at a stellar halo with sufficient depth is to look at the accumulated record of everything that happened to a galaxy across most of its history. The faintest, most diffuse structures are the oldest. The brightest, most coherent streams are the most recent. In between, the halo holds traces of encounters at every scale and every age, layered and mixed but not entirely lost, readable with sufficient care. Tidal structures, then, are not merely the byproduct of collisions. They are the evidence. They are what gravity writes in stars when galaxies pass close enough to grip each other, and they persist, in one form or another, for as long as the stars within them can be distinguished from the surrounding field. The tails that sweep outward during a first pericentric passage are the most dramatic expression of this writing, long, luminous, immediately visible, even in images taken by amateur telescopes when the system is close enough and the tails bright enough. But the dispersed remainder of those tails, the shells and streams and halo overdensities that persist for billions of years after the merger is complete, carry the same information in a more patient form. A slow fade is still a record. The antennae galaxies, in their current state, display the early phase of this process. The tails are still bright, still coherent, still sweeping outward in their long symmetric arcs. The two nuclei are still distinct within the overlapping halo. The system is, in the language of dynamics, still in the process of merging. The first pericentric passage is complete. The two galaxies are now falling back toward each other for a second and eventually final coalescence, and the tidal tails that were produced during the first pass are still spreading, still bright enough to trace from end to end with a modest telescope under dark skies. In a few 100 million years, the nuclei will have merged. The spiral structures that still faintly mark the disks of the two progenitors will have been mixed and phase averaged into the smooth stellar body of the merged system. The bright overlap region will have settled or dispersed, and the tidal tails will have faded, their stars spread through the growing halo of what is now a single, larger, rounder galaxy. What will remain of the tails will not be visible as tails. It will be visible as a halo, diffuse, extended, slightly asymmetric in ways that point to the geometry of the encounter that produced it. And within that halo, if any instruments capable of measuring individual stellar velocities and chemical abundances ever examined it from outside, there would be streams, faint, ancient streams, each one encoding the orbit of a passage that happened when the universe was younger. In the outer halo of the merged antennae remnant, the tidal dwarf galaxies that condensed at the tips of the original tails may still be present as small coherent overdensities, or they may themselves have been disrupted by subsequent encounters and their material redistributed into the halo. Their fate depends on how massive they became before the tidal field of the growing merger remnant reached them, and on how many times the tidal field has varied in strength and direction as the merger progressed. Some will survive for billions of years as small dark matter poor stellar systems. Some will dissolve. The distinction between survival and dissolution for a tidal dwarf galaxy comes down to mass and timing and orbital geometry in proportions that simulations can estimate, but observations can only slowly constrain. The universe is patient with these processes. There is no deadline for the dissolution of a tidal tail. There is no moment when the stars within it are reclaimed or recycled. They simply spread and continue spreading, following their orbits through the growing halo of the merged system, their positions shifting imperceptibly from century to century, their light unchanged, their motion encoding the ancient push that sent them outward when two galaxies first came close enough to grip each other. A tail that formed 300 million years ago is still spreading now. The stars within it are still moving. They will continue moving for longer than any telescope currently in existence, or any telescope likely to be built within any human era, will be able to follow. The spread will continue until the stars are too diffuse to distinguish from the halo, and then the halo itself will continue to spread as the merged galaxy ages, its outer edge slowly thinning, the outermost stars drifting gradually toward the escape velocity of the local gravitational field. The farthest flung stars from the oldest tidal tails will, in time, cross into the intergalactic space between galaxies and continue outward from there, their motion carrying them away from everything they once belonged to at speeds that gravity can slow, but not eventually reverse. These are the intergalactic stars, and they exist in large numbers in galaxy clusters, stars that no longer orbit any galaxy, moving through the space between galaxies in slow, ancient, unattached paths. Many of them are there because of tidal tails. The tidal forces that produce those tails are the same forces that have been shaping galaxy morphology since the first close encounters early in the universe's history. Every large elliptical galaxy carries in its stellar halo the record of every merger that built it. Every stream in the halo is a dissolved tail. Every shell, those faint arc-shaped overdensities that appear around some elliptical galaxies, like the concentric rings left by a stone, dropped in still water, is the wrapped remnant of a disrupted satellite's stars, phase mixing into the host's potential well, at a rate so slow that the shell structure persists for billions of years before washing out entirely. Shells, streams, and halo overdensities are the long memory of galactic violence, and they are everywhere. Any galaxy old enough and massive enough to have undergone multiple mergers across its history carries this record in its outer light, available to any survey patient enough to look. The Sagittarius stream wraps around almost the entire sky, not because the interaction is dramatic in the usual sense. It is slow, it is old, it is already mostly complete, but because the satellite it came from has been orbiting for long enough, and at the right inclination to deposit its stripped material across a great looping arc. The stream is beautiful in the data, in the plots of star positions and velocities that reveal its shape against the background of Milky Way field stars. It has no color in the way a nebula has color. It has no glow in the way a star-forming region glows. It is visible only in the statistical excess of stars at a particular velocity and chemical abundance, spread across a region of sky so large that seeing it all at once requires reducing the entire hemisphere of the galactic sky to a diagram. That diagram is the stream, and within that diagram, the orbital history of the Sagittarius dwarf galaxy, how it fell in, at what angle, over how many orbits, is encoded in the shape of the stream and the way it wraps, Models that simulate the orbit of the Sagittarius dwarf through the Milky Way's gravitational field and compare the resulting simulated stream with the observed one can constrain the mass and shape of the Milky Way's dark matter halo in ways that no other method so easily provides. The tidal debris of a disrupting satellite is, in this way, a probe of the gravitational potential that produced it, not just a record of the satellite's fate, but a tool for measuring the invisible architecture of the host galaxy. The dark matter halo of the Milky Way is otherwise very difficult to weigh and map. It extends hundreds of thousands of light years beyond the visible disk, its mass far exceeding the total mass of all the stars and gas the Milky Way contains. But it emits nothing. It reflects nothing. It interacts with ordinary matter only through gravity. The stellar streams that wrap through the halo, each one following the shape of the potential well that contains it, trace the dark matter distribution in 3 dimensions, not directly, but by implication. The stream is bent by the dark matter, shaped by it, and by matching the observed shape of the stream to models of what different dark matter distributions would produce, the dark matter can be constrained from the outside. In this way, the destroyed satellite becomes the instrument for understanding what destroyed it. The material in a tidal tail does not stop telling its story when the tail fades. It continues in the halo, in the shells, in the stream, in the orbital parameters of stars that were once part of another galaxy and now move through the outer reaches of a much larger one. The story is long and slow and quiet, but it is there, written in light and motion and the measured abundances of elements in old stars, available to those with the tools to read it and the patience to look long enough. When the gas within a dense knot near the tip of a tidal tail begins to pull itself together, when the local density has grown high enough that the self-gravity of the gas begins to dominate over the tidal forces trying to pull it apart, something changes. The knot contracts. It cools as it contracts, the gas radiating away the energy of compression, growing denser still. Stars begin to form within the cooling gas, small at first, then larger, then the full range of stellar masses that any region of collapsing gas will produce, given sufficient time and material. The knot is no longer just material from a disrupted outer disk flung into the space between galaxies by a tidal encounter hundreds of millions of years ago. It is a galaxy, small, perhaps only a few million stars, perhaps lacking the dark matter scaffolding that underlies almost every other galaxy in the universe, perhaps already in a gravitational relationship with the merged remnant of the two systems that produced its parent tail, but coherent, self-gravitating, making its own stars from its own gas, moving through space as a distinct object with a center of mass and a velocity and an identity that is for the time being its own. The tidal forces that stripped it from a galaxy and flung it outward also, in the end, concentrated it. Destruction gave it the conditions for formation. The material flung furthest from its origin gathered into something new. In the quiet at the outer edge of a long fading tidal tail, something that did not exist before the collision began to exist because of it. Not a remnant of what was there. Something genuinely new, made of old stars and enriched gas, born in debris, orbiting slowly at the far end of a luminous arc that is already beginning to fade. Two vast clouds of gas approach each other in the dark. They have been drifting toward this moment for millions of years, each carried by the slow inward pull of two galaxies whose outer halos began overlapping long before their luminous disks drew anywhere near. The clouds are cold in the way that space between stars is cold, not a temperature felt on skin, but a temperature so far below anything living that the molecules within them barely move at all, suspended in a quiet so deep it has no name in any human language. And then the first edge of one cloud meets the first edge of the other, and the quiet ends. The collision does not happen all at once. It happens the way a tide moves, not as a wave crashing, but as a slow, unstoppable rising, as pressure builds along a front that stretches across thousands of light years. Along that front, gas that has drifted unchanged for hundreds of millions of years is suddenly compressed. The temperature climbs, the density climbs, and in the densest places, where the compressed material thickens beyond a threshold that gravity has been waiting for, something begins. Stars form. Not one, not 10, not 1,000. They form in their millions, igniting across the shocked front like a wave of quiet fires, spreading through material that has been waiting, without knowing it, for exactly this pressure. The rate of this birth is not the slow, steady trickle that characterizes an ordinary galaxy moving through its ordinary life. It is something far more prolific, star formation rates tens of times, sometimes 100 times, higher than a galaxy like this would sustain on a calm and ordinary day. The merger has done what no quiet passage through open space could do. It has breached the threshold everywhere at once. This threshold has a name drawn from the physics of gravitational instability. A cloud of gas, spread thin and cold, resists its own gravity through thermal pressure and rotation, but compress it fast enough, raise its density past a certain point, and the pressure can no longer hold. Gravity wins, locally, suddenly, across the entire compressed region at the same moment. The threshold it crosses carries the name of the physicist who first described it mathematically, James Jeans, who worked through the conditions for collapse more than a century ago and could not have imagined the scale at which his equations would one day be applied. In a merging pair of gas-rich galaxies, the Jeans instability is not crossed in one place. It is crossed across a region spanning thousands of light years in hundreds of collapsing pockets simultaneously, and the result is a starburst, a galaxy that has been startled into creating stars faster than at any other time in its life. The compressed front glows. In the wavelengths of visible light, it is partly hidden. Dust is thick where the gas is dense, and dust swallows light the way deep water swallows a stone, letting nothing out. But in the longer wavelengths of infrared light, the dust itself becomes the signal. The newly formed stars pour their energy into the dust that surrounds them, and the dust warms and re-radiates that energy outward as a broad glow of thermal infrared emission, a signal that says, here, hidden inside all of this, something enormous is underway. Instruments built to read this wavelength have revealed that some of the most luminous objects in the nearby universe are not the brightest in visible light. They are among the dimmest. They are galaxies whose faces in ordinary light seem unremarkable or disturbed or simply dark, and yet in infrared they outshine 1,000,000,000,000 suns. 1,000,000,000,000 suns. That number sits quietly on the surface of understanding and resists any attempt to feel it fully, so it is better approached from one side at a time. A galaxy of ordinary productivity, something like the Milky Way on a calm year, forms stars at a rate of perhaps 1 or 2 solar masses per year. A starburst galaxy, in the middle of a gas-rich merger, can form stars at a rate of 50, 100, 200 solar masses per year. The total light output of all those newborn and forming stars, absorbed by dust and re-emitted as heat, accumulates until it exceeds the combined luminosity of every ordinary star in an entire large galaxy by a factor of 10 or 100 or more. This is not brightness performed for effect. It is what physics produces when you compress enough cold gas fast enough in a small enough region and let gravity take everything it is owed. The category name for these objects is ultraluminous infrared galaxies. The threshold that places a galaxy in this category is an infrared luminosity of at least 10 to the 12th times the luminosity of the Sun, 1 trillion solar luminosities, emitted in the thermal glow of heated dust. Some are more luminous still, by factors of 10 or more, pushing into the regime of hyperluminous infrared galaxies, a category so extreme that objects qualifying for it are rare even across the entire observable universe. The first time anyone knew these objects existed came in 1983 when a satellite was launched, whose instruments were cooled to within a few degrees of absolute zero so they could detect the faint warmth of distant galaxies without their own heat drowning the signal. That satellite scanned the entire sky in infrared wavelengths over the course of 10 months. What it returned was a catalog of sources, points, and smears of infrared emission that included, for the first time, a population of objects no one had expected in such numbers. Galaxies that appeared perfectly ordinary in photographs taken through optical telescopes showed up in the infrared data as among the most luminous sources in the sky. Follow-up observations told the rest of the story. Almost every one of these extreme infrared sources, when examined carefully, proved to be a pair of galaxies in the middle of a collision or a late-stage merger whose two nuclei had not yet fully combined. The link between major mergers and ultraluminous infrared emission was not gradual or ambiguous, it was immediate and nearly universal. The satellite's catalog settled the question before anyone had finished asking it. In the years that followed, astronomers turned their sharpest instruments toward these infrared brilliant systems, and what they found confirmed and deepened the picture. The ultraluminous infrared galaxies were not exceptions or accidents. They were what gas-rich major mergers looked like from the outside, from the perspective of a distant observer whose instruments could peel back the dust and count the photons that the interior was pouring out in the form of reprocessed thermal radiation. Visible light told almost nothing. Infrared told nearly everything. And radio wavelengths, sensitive to entirely different physical processes, added details that completed the picture in ways that visible and infrared observations alone could not. At radio wavelengths, the interior of a starburst is a different kind of bright. Where infrared reveals the warmth of heated dust, radio emission from a starburst traces something more specific, the remnants of massive stars that formed in the burst, burned through their fuel, and exploded. A star many times more massive than the Sun does not live long. It forms in a compressed cloud, fuses hydrogen to helium, helium to heavier and heavier elements, until at the end it collapses and then detonates in a supernova, an explosion that scatters its enriched interior across the surrounding gas and leaves behind a rapidly spinning stellar corpse. A neutron star emitting radio waves in steady pulses while its surrounding ejected material spreads outward as a shell of glowing ionized gas. Inside a galaxy whose star formation rate is 100 times the norm, supernovae are occurring at a rate 100 times higher than normal. The interior of such a galaxy, mapped at radio wavelengths, shows these remnants scattered across its central region like cooling embers from a fire that has been burning fast and hard for millions of years. The closest ultraluminous infrared galaxy to our own position in the universe sits roughly 250 million light-years away. It is a distance so large that the light now arriving from it began its journey before the first dinosaurs appeared on Earth. The galaxy is known by its catalog designation, ARP 220, a name that carries the slightly impersonal character of all catalog names, saying only that it was included in a particular astronomer's atlas of peculiar galaxies compiled in the 1960s, without describing what it looks like or why it ended up in that list. What it looks like to optical telescopes is a compact and disturbed object, clumpy, asymmetric, wrapped in a shell of older stars that extends in faint loops and arcs away from the bright central region, the morphological signature of two galaxies that have already been through their pericentric passages and are now finishing the process of merging into one. The two original galactic nuclei have not fully merged. They sit separated by a small distance, small by galactic standards, only a few hundred light years, each surrounded by a dense rotating disk of molecular gas and dust, so thick that almost no visible light escapes from either of them. In these two inner disks, something close to the limit of what a starburst can produce is playing out. The star formation rate within ARP 220 is estimated at something between 50 and 200 solar masses per year, a range wide enough to reflect genuine measurement difficulty. Because the interior is so buried in dust and churning gas that no single method of measuring star formation gives a clean answer. Radio observations reveal a population of radio supernovae, the expanding radio bright shells of exploded massive stars, so numerous that new ones have appeared within the time spans of observational campaigns. The rate of these supernovae implies a rate of massive star formation that, sustained across millions of years, would have already converted a significant fraction of the available gas into new stars. And yet the gas reservoirs in both inner disks remain enormous, sustained partly by the dynamics of the ongoing merger, still funneling material toward the center. Outside the two dense inner disks, the broader region of ARP 220 is not quiet. The outer envelope of stars, the remnant of the original spiral disks that once existed before the merger destroyed them, extends in faint light for tens of thousands of light years around the bright central system. In this envelope are shells and loops of stars, the gravitational debris of two disk galaxies that orbited each other, disrupted each other, and are now settling into a new and different shape. The shells are faint. They require careful observation to distinguish from the sky around them. But they are there, and they encode in their positions and velocities the entire history of how two separate systems fell together and became one. Farther out still, at radio wavelengths sensitive to the cold neutral hydrogen gas that lies in the outer regions of galaxies, there is evidence of material that was once in the outer disks of the original galaxies and has been thrown into long arcs by the same tidal forces that in younger merging systems produce the sweeping tidal tails visible in optical images of systems like the antennae. In ARP 220, which is much further along in the merger process, these arcs are not the prominent luminous tails seen in freshly colliding pairs. They are broader, more dispersed, the remnants of tidal structures that formed and are now dissolving back into the growing merged system. What was thrown wide is being drawn back inward. It always is, eventually. The antennae galaxies are a different kind of window into this same set of processes. They are far younger in their merger sequence than ARP 220, their two nuclei still separated by thousands of light years, their tidal tails still sweeping outward in long, graceful arcs visible in every optical image of them, their collisions still producing active shocks and compression rather than a single settled remnant. In the overlap region between their two disks, the zone where gas from one galaxy has met gas from the other and compressed, star formation is vigorous, not as extreme as in ARP 220, whose merger is more advanced and whose gas has been concentrated into a smaller volume over a longer time, but active enough to produce young clusters of stars shining with the blue-white light of newly ignited massive stars embedded in knots of ionized hydrogen gas that glow in the red light of excited hydrogen atoms being struck by ultraviolet radiation from the stars they surround. Within those knots, among the brightest and most compact, are objects that represent something more than ordinary star formation. These are superstar clusters, concentrations of millions of stars packed into a region only a few light years across, held together by their own gravity, shining with a combined intensity that makes them visible across tens of millions of light years, even at the resolution limits of the Hubble Space Telescope. A superstar cluster of this kind is not a loose association of young stars scattered across a large molecular cloud. It is a gravitationally bound object, a thing that, if left undisturbed, might persist for billions of years, slowly aging as its most massive stars exhaust their fuel and die, its less massive stars enduring long after the merger that created it has been forgotten by the universe. The connection between superstar clusters and the ancient globular clusters that circle galaxies today is not a settled question, but it is a compelling one. Globular clusters are among the oldest objects in any galaxy, gravitationally bound spheres of hundreds of thousands to millions of stars, formed early in cosmic history when conditions across the universe were more extreme than they are now, when gas densities were higher and star formation more violent. They orbit the galaxies they belong to as ancient remnants of the conditions that made them and the physical conditions that produce superstar clusters in the merging antennae look, in some important ways similar to conditions thought to have prevailed when the ancient globulars were born. Whether the clusters forming today in merging galaxies will survive long enough and intact enough to become the globular clusters of future epochs is uncertain. Some will dissolve, some will be disrupted by the gravitational turbulence of the ongoing merger. A few may persist. The life of a massive star inside one of these clusters is brief by any cosmic measure, though not brief enough to be felt as anything other than vast by human reckoning. A star of 30 or 40 solar masses, the kind that forms readily in the compressed gas of a starburst, burns through its hydrogen fuel in a few million years, fuses its helium into carbon, its carbon into oxygen and neon and magnesium and silicon, pressing closer and closer toward iron, which cannot release energy through fusion and so represents the end. When the core reaches iron, fusion stops. The core collapses in under a second. The outer layers fall inward, rebound off the collapsed core, and explode outward in a supernova whose luminosity briefly rivals a billion suns. And in the gas and dust that surrounds this dying star, the shock wave of the explosion does something to its environment. It compresses the surrounding material, possibly triggering the formation of a new generation of stars in the compressed shell around the supernova remnant. This is how a starburst propagates through a galaxy, not as a single synchronized wave, but as an overlapping cascade of triggered events, each supernova and each expanding shell of hot gas, adding momentum and pressure to the surrounding material, alternately dispersing it and compressing it, carving bubbles of hot ionized gas into the interstellar medium, while piling up denser regions at the bubble walls where new stars can form. The starburst is not a single moment. It is a prolonged, self-perpetuating storm in which the deaths of the most massive stars create conditions that allow the next generation to begin. But the storm cannot sustain itself forever. The gas that feeds it is finite. As the starburst consumes the available molecular gas, converting it into stars, dispersing some of it as hot outflows driven by the combined energy of thousands of supernovae, and heating the rest until it rises out of the densest regions. The conditions for rapid star formation gradually become less favorable. The dense cold gas clouds thin, the rate of collapse events slows, new massive stars become rarer. The supernovae that had been occurring constantly, renewing the energy of the interstellar medium and triggering new collapse events become less frequent. Across millions of years, the starburst winds down, not all at once, not sharply, but in a slow declining curve whose shape can be read from the light of the remnant galaxy, long after the burst itself has ended. The way that light carries this record is specific and quiet. A galaxy in the middle of a starburst blazes blue, its light dominated by the hot, luminous, short-lived massive stars that burn through the high end of the mass spectrum first. As those stars die, the blue fades and the galaxy's light shifts toward the yellower tones of stars with less mass and longer lives, stars that form during the burst but will outlast it by billions of years. There is, in the aftermath of a starburst, a spectral signature that astronomers have learned to recognize, an excess of light at particular wavelengths produced by a population of moderately massive stars, the A-type stars, white and slightly warm, that formed in the burst and have outlived their more massive siblings, but have not yet aged enough to fade toward the yellow and orange of smaller, older stellar populations. A galaxy bearing this spectral signature is called a post-starburst galaxy, or sometimes by the shorthand E plus A, for the way its spectrum combines features typical of an elliptical galaxy, dominated by older stellar light, with an excess of the absorption lines characteristic of these intermediate A-type stars. The A-type stars are the evidence left behind after the more massive stars have already died, and they will themselves fade over the next billion years or so, as they too exhaust their fuel and become cooler, dimmer remnants. The spectral signature of a post-starburst galaxy is a clock, in a sense, a clock that started when the burst began and is running down toward the time when the last traces of the burst will be indistinguishable from the light of an ordinary aging stellar population. There is something calm in imagining this, a galaxy that was once pouring out the light of a trillion suns, hidden behind its own dust, now aging quietly into the shape of a system that shows only traces, only the spectral whisper of the A-type stars, steadily cooling and dimming, of what it once was. The burst consumed itself. It left behind a new population of stars, many of which will persist for billions of years, enriching the gas around them with the heavier elements, their interiors forged and scattered outward in their deaths. Iron, oxygen, carbon, silicon, calcium, the elements produced in stellar interiors and distributed through supernova explosions, accumulate in the interstellar medium of the merger remnant, raising the chemical richness of the gas available for any future generation of star formation. Each episode of intense star formation leaves the galaxy chemically richer than it was before. Inside the densest, most chemically enriched knots of the starburst region, the stars that form are themselves richer in these heavier elements, what astronomers call metals, using the term broadly to mean everything heavier than helium. These enriched stars, when they eventually form planets around them, have more raw material available for the construction of rocky worlds. The connection between the violence of a starburst, an emerging galaxy, and the eventual, much quieter possibility of rocky planets orbiting individual stars inside the remnant is not a short chain. It runs through the chemistry of the interstellar medium, through the aggregation of enriched dust grains into solid bodies, through the entirely separate physics of planetary formation around individual stars. But the chain exists. The prolific creation of stars in the compressed shock fronts of a galactic merger leaves a chemical legacy in the medium those stars enrich, and that legacy persists long after the last echoes of the merger have been smoothed away by time. The dust that made the starburst invisible in optical light is itself a product of earlier stellar generations, carbon grains, silicate grains, ice-coated particles that formed in the cool outer layers of aging giant stars and were expelled into the interstellar medium over billions of years before the merger began. The merger compressed this dust along with the gas, concentrating it in the regions where star formation was most intense, wrapping the new stellar nurseries in layers of absorbing material that blocked visible light and forced the energy of the burst to be re-emitted in the infrared. In the aftermath, as the gas and dust disperses, driven outward by the collective pressure of thousands of supernovae and the thermal energy of the hot gas they leave behind, the merger remnant gradually becomes more transparent. The stars formed in the burst become visible to optical instruments. The remnant brightens in optical wavelengths as the obscuring material thins, and what emerges from behind the dust is a system that looks to optical telescopes like an elliptical or lenticular galaxy in the making, smooth, slightly asymmetric, wrapped in faint loops and shells that are the visible record of the collision. The faint loops and shells around post-merger elliptical galaxies have been studied carefully enough to function as a kind of archaeological record, a way of reading from the present structure of a galaxy something about the collision history that produced it. The shells form when stars from the infalling galaxy spread out and oscillate around the center of the combined system, arriving at their maximum distance and momentarily piling up before falling back inward, creating thin, overdense arcs that can persist for billions of years before phase mixing dissolves them into the background. A smooth elliptical galaxy surrounded by such shells is one that merged, and the number and geometry of the shells carries information about how many times material has piled up at particular radii, information about orbital parameters, mass ratios, and timing that is in principle readable by someone patient enough to look and careful enough to interpret. The most massive merger remnants in the local universe, the giant elliptical galaxies that sit at the centers of large clusters of galaxies, are thought to have grown through repeated episodes of this kind. Not one merger, but several, accumulated across cosmic time, each one adding stars and triggering a burst of star formation, and then quieting, leaving behind a slightly larger, slightly more chemically enriched system. The giant elliptical galaxy at the center of a cluster today is in some sense a palimpsest, a document written over many times, each merger episode overwriting some of the structure left by the previous one, leaving only the broadest features of the earliest collisions visible in the outer halos and the chemical gradients of the stellar population. The outer halos of these systems are faint. They require long exposures and careful sky subtraction to detect, because they are only slightly brighter than the darkness around them. But in those faint halos distributed across hundreds of thousands of light years, the stars from all the previous mergers are distributed, mixed and dispersed into broad, smooth profiles that no longer carry the tight structural signatures of the individual galaxies they came from. They drift there now, in the outer halos of enormous elliptical galaxies, orbiting slowly in the gravitational well of a system built from many systems across billions of years, indistinguishable from each other by any measurement currently available, their origins lost in the averaging of orbital phase space. Within the compressed gas that starburst galaxies pour toward their own centers, another kind of physics is beginning, a physics that belongs to the feeding of the supermassive black holes that sit at the centers of both galaxies involved in the merger. That thread runs deep and will carry its own consequences. But the stars themselves, the simple chemical transformation of cold gas into glowing plasma through the brute force of compression and gravity, that process is complete in itself, and its products endure. A star formed in the starburst of a major merger 10 billion years ago is, if it was not too massive, still burning today. Its light crosses the space between it and any observer who happens to look in its direction. The energy it produces moment by moment comes from the fusion of atoms in its core, atoms that were gathered from the compressed cloud that gravity collapsed in a galaxy that no longer exists as a separate structure, in a collision that ended billions of years ago and left no trace in the night sky that any human eye can detect without the aid of instruments tuned to the faintest light. The starburst ends. The light from the most massive stars fades. The A-type stars remain for a while, cooling slowly, their spectral signature growing fainter over hundreds of millions of years, until even that faint record of the burst is no longer distinguishable from the ordinary aging glow of an old stellar population. The merger remnant settles. Its stars find their orbits in the new gravitational well of the combined system. The dust disperses or accretes into new stars, or into the disks of planets forming around them. The chemical richness of the interstellar medium, raised by all those supernova explosions, all those massive stars that formed and died in the burst, slowly spreads through the new system, gradually mixed by the slow circulation of gas across millions of years, and in the places where the shock front was densest, where the gene's threshold was crossed first and most thoroughly, the oldest stars from that burst are now deep inside the merger remnant, not easily distinguished from the other stars around them, their origins encoded only in their chemical composition, in the particular ratios of elements in their spectra that reflect the history of the gas from which they condensed. They carry that chemical memory the way old stone carries the memory of the conditions in which it formed, not in any signal that announces itself, but in a quiet physical fact, readable only by instruments patient and precise enough to ask the right question. The energy that created them came from compression. The compression came from a collision. The collision came from gravity, the long, slow, patient force that acts across any distance, that never stops, that does not need a deadline or a reason. Two gas-rich galaxies fell toward each other through the dark, and where their cold gas met, something ancient and simple happened. Matter gathered, stars formed. Some burned brightly and briefly, and exploded, scattering the elements they had built into the medium around them. Others burned more slowly and are burning still. The light of all those stars, the ones that died in the burst and the ones that outlasted it, has been spreading outward through space ever since, at the only speed light knows, in every direction, without preference or purpose. Some small fraction of it falls, after millions of years of travel, onto the surfaces of instruments that human beings have built and pointed carefully at the sky. What those instruments return is not the drama of the collision that is long over, but its quiet aftermath, a smooth oval of aging light, faintly chemical in its spectrum, surrounded by loops and arcs of dispersed stars, slowly continuing to orbit and cool and drift in the deep and unhurried dark that has been there all along. Deep within a galaxy already shaped like a slow bruise across the sky, 2 points of hard light burn from separate centers. They are separated by thousands of light years. Each sits at the heart of its own whirlpool of gas and dust, drawing matter inward, heating it past any temperature a star's core could reach, and blazing in frequencies no human eye can receive without instruments built for the purpose. From far enough away, the galaxy that holds them looks like a single disturbed thing, its arms pulled out of symmetry, its dust lanes bent and folded, where two vast systems have already drawn into each other's gravity and begun the long work of becoming one. But look more closely through a telescope tuned to the hardest X-rays, and the two nuclei resolve into separate sources, two engines, two ancient accumulations of mass, each millions or billions of times the weight of the sun, each still surrounded by its own spinning disk of falling material, still feeding, still blazing, separated now only by the slow shrinking distance between them. This is what a late-stage merger looks like at its most hidden center. The stars have already begun to mix. The gas clouds have already collided and compressed and driven new star formation across regions spanning tens of thousands of light years. And at the core of all of it, the two most massive objects either galaxy ever held are still sinking toward each other, separated by a distance that sounds small only against the scale of the universe, a few thousand light years, or a few hundred, or a few dozen, still too far to be called a binary, still too close to be called anything else. What happens to them is one of the deepest, slowest, and most consequential events in all of galactic history. It unfolds across hundreds of millions of years. It produces no light that travels quickly to the eye. It sends its signals through the shape of space-time itself, at frequencies so low that detecting them requires an instrument the size of the galaxy. And the process that drives it, the invisible transfer of motion into the surrounding field of stars and dark matter, is the same process that has been drawing these two galaxies together since long before their luminous disks first swept past each other. When two galaxies merge, both of their central supermassive black holes eventually end up within the same gravitational system. At first, they are separated by many thousands of light years, each sitting near the center of its own progenitor galaxy's remnant, still surrounded by the stars and gas that once orbited it alone. The host galaxies around them have already begun to phase mix, the stars from each system passing through the other, their original orbits scrambled by the new combined gravitational potential. But the black holes are dense, they are compact. Their orbits decay more slowly than the stars around them, and so for a long time they continue circling each other through the merged stellar body like two stones sinking at different rates through the same deep water. Astronomers can identify these pairs while they are still separated. In galaxies hundreds of millions of light years away, the two bright nuclei show up as distinct X-ray sources in images taken by the Chandra Observatory, a telescope in orbit above the distorting atmosphere, tuned to the high-energy radiation that only active galactic nuclei and certain violent stellar remnants produce at that intensity. The two sources sit close together on the sky but not touching, two hard, faint points of light within a single blurred and disturbed host galaxy, their separation measurable in kiloparsecs, which is to say in thousands of light years, which is to say in a distance still vast, even by galactic standards. Optical spectroscopy of the same systems sometimes reveals two distinct sets of emission lines, each shifted by a different velocity, each belonging to a different nucleus, still moving at its own speed within the merged body. Radio interferometry can resolve the structure further still, tracing the jets and lobes of material that active nuclei sometimes produce, confirming that both sources are real and separate, and active. The two nuclei are classified as dual active galactic nuclei. Each is a supermassive black hole currently feeding, surrounded by an accretion disk of hot, spiraling gas, driving radiation outward in all directions, sometimes launching narrow jets of accelerated material along its rotation axis. They are not yet a binary in any gravitational sense. They are simply two massive objects within the same galaxy, each orbiting the combined center of mass of the system they now share, drawn together slowly by the same mechanism that has been shaping the merger from the very beginning. That mechanism is dynamical friction, not the friction of surfaces touching, but a subtler process, the gravitational stirring that a massive object produces as it moves through a field of smaller masses. Every star near the path of a sinking black hole feels a small tug toward it as it passes. The star accelerates slightly, gains a tiny amount of energy, and falls just slightly outward in its orbit. The black hole, by the same principle that governs all such exchanges, loses exactly that energy. It slows. It falls inward. The process is cumulative. Across millions of years and millions of interactions with individual stars, the black hole loses enough orbital energy to sink measurably closer to the center of the merged system. If there are two black holes sinking through the same field of stars, they sink toward each other as well, their mutual orbit tightening decade by decade in a way no single human lifetime could detect, but that simulations and theory trace with confidence. This sinking continues until the two black holes reach a separation of roughly a parsec, a distance of about 3 light years, which is nearly nothing by galactic standards. At that scale, the black holes are close enough to be a true gravitational binary, orbiting each other on a timescale of years rather than millions of years. But here, the process that drove them together begins to run out of material to work with. The mechanism of dynamical friction requires stars passing close enough to be gravitationally stirred. In the dense inner region of a merged galaxy, the black hole binary has already scattered most of those stars outward, ejecting them from the loss cone, the range of orbits that would bring them close enough to interact. Once those orbits are depleted, the supply of stars available to carry away the binary's orbital energy is sharply reduced, and the inspiral slows, perhaps dramatically. This is the problem that theorists call the final parsec. The two black holes, after a journey of billions of years and thousands of light years, find themselves stalled at the edge of true coalescence, close enough to orbit each other in years, but apparently without a mechanism to carry them. The last short distance to merger, the final parsec, has been a genuine open question in theoretical astrophysics for decades. Gas inflow from the surrounding merger remnant may help, molecular gas driven inward by the turbulent dynamics of the collision could form a new disk around the binary, and the gravitational interaction between the binary and that disk could carry away angular momentum more efficiently than stars alone. A third black hole, brought in by a subsequent minor merger, could perturb the binary's orbit in ways that accelerate coalescence. Triaxial stellar potentials, the non-spherical, asymmetric shapes that merger remnants often have, may replenish the loss cone through chaotic stellar orbits that refill it from unexpected directions. No single solution has been confirmed. The best current picture is that some combination of these effects, varying from system to system, eventually carries the binary through this last barrier. The observational evidence suggests that mergers do complete, that binary black holes do eventually coalesce, because the universe contains the gravitational wave signal that only their mergers can produce. When two supermassive black holes finally spiral together and merge, they produce a burst of gravitational radiation, not the brief, sharp chirp that comes from two stellar mass black holes, the kind detected by ground-based instruments sensitive to frequencies of tens to hundreds of cycles per second. The merger of two black holes, each carrying hundreds of millions or billions of solar masses, radiates at frequencies enormously lower, cycles per year or per decade, corresponding to wavelengths so long that detecting them requires a baseline the size of the galaxy itself. A single observatory cannot span that distance, but the galaxy provides one, scattered across the Milky Way, at distances of hundreds to a few thousand light years from Earth. There are pulsars, compact stellar remnants left behind when massive stars collapsed at the ends of their lives. The most useful are the millisecond pulsars, ancient objects spun up to extraordinary rotation rates by accreting matter from companion stars over hundreds of millions of years, now rotating hundreds of times per second with a mechanical regularity that rivals the best atomic clocks ever built. Each rotation produces a narrow beam of radio emission that sweeps past the Earth at predictable, extraordinarily stable intervals. If nothing disturbs the space between the pulsar and the radio telescope receiving its signal, the pulse times arrive on a schedule that can be predicted years or decades into the future, with only tiny corrections needed. A gravitational wave passing through the galaxy stretches and compresses space itself as it moves. The distances between the pulsar and the telescope along each line of sight fluctuate by the tiniest fractions of a light year, amounts that are genuinely small even by the standards of things measured in light years. But the pulsars are precise enough to feel it. A gravitational wave passing through the array of pulsars leaves a signature. Timing residuals, tiny systematic deviations from the predicted arrival times of pulses that are correlated between different pulsars in a specific geometric pattern. Two pulsars in roughly the same part of the sky should show correlated residuals. Two pulsars on opposite sides of the sky should show anti-correlated ones. This pattern, called the Hellingsdowns curve after the researchers who first calculated it, is the unmistakable fingerprint of a gravitational wave background permeating the galaxy. For decades, teams of researchers at radio telescopes on multiple continents observed dozens of millisecond pulsars simultaneously, accumulating years of timing data with the patience that only astronomy at its most demanding requires. The North American Nanohertz Observatory for Gravitational Waves, the European Pulsar Timing Array, the Parkes Pulsar Timing Array in Australia, and the Indian Pulsar Timing Array all pursued the same signal through the same long years of observation. The work required exquisite calibration. Every effect that could alter the pulse arrival times, the motion of the Earth around the Sun, the motion of the Sun through the galaxy, the dispersion of radio waves by electrons in the interstellar medium, the irregular rotation of the Earth itself, had to be modeled and removed. What remained, if there was a signal, would be the faint imprint of gravitational waves. In 2023, those collaborations announced converging evidence. The timing residuals in their data showed the spatial correlations that the Hellingsdowns pattern predicts. The signal was not from a single source, not from one nearby supermassive binary announcing itself with a clean periodic wave. It was the superposition of signals from an enormous number of merging supermassive black hole systems distributed across the observable universe, their individual contributions blending into a background hum, a stochastic wash of gravitational radiation arriving from all directions at once. Each contributing merger was too far away and too faint to be individually resolved. Together they produced a background just strong enough, across a decade of careful observation, to rise above the noise. What the pulsar timing arrays heard in that first careful evidence was the accumulated gravitational sound of a cosmological population of merging supermassive black holes. Every galaxy collision across billions of years of cosmic history in which the two central masses eventually spiraled close enough to radiate at nanohertz frequencies. The signal encoded the history of galaxy mergers across time, how often mergers occurred, across what range of black hole masses, distributed through what epochs of cosmic history. Theorists could compare the measured background to predictions based on galaxy merger rates and black hole mass distributions, and the early comparisons were broadly consistent with the picture already understood from other lines of evidence. The universe of colliding galaxies had been sending this signal for billions of years. In 2023, for the first time, instruments on Earth were sensitive enough to begin to hear it. There is something very quiet about that kind of detection. No alarm sounded. No flash of light arrived. The signal was found in tables of timing residuals, in the shape of a correlation function plotted across pulsar pairs, in the slow convergence of measurements taken over years. It was patient work meeting a patient signal, the trembling of spacetime from the most massive gravitational events in the universe, finally meeting instruments careful enough to receive it. The black holes that drive this signal are not passive. While they are sinking toward each other and while they are orbiting as a binary, the more massive of the two, or both in gas-rich mergers, may still be actively feeding. Gas driven inward by the tidal distortions and turbulence of the merger can reach the accretion disk surrounding each nucleus. As it spirals in, it converts gravitational potential energy into radiation with an efficiency that no other known process approaches. A fraction of the infalling mass, somewhere between a few percent and more than 10%, depending on the geometry and the black hole's spin, is radiated away before it crosses the event horizon. At the luminosities involved, this means that a single actively feeding supermassive black hole can outshine the combined light of hundreds of billions of stars, everything else in the galaxy added together. This radiation does not simply glow outward harmlessly. It interacts with the gas around it. Photons carry momentum, and when they are produced in sufficient numbers, they push on the gas that surrounds the nucleus. Powerful radiation fields can drive material outward, not gently, but at speeds of hundreds or even thousands of kilometers per second, far exceeding the escape velocity of the galaxy's central region. This process, called feedback, carries energy and momentum from the accreting nucleus into the surrounding interstellar medium. Broad outflows of ionized gas can be traced optically in some systems, their Doppler broadened emission lines marking material flying outward at velocities no stellar process could produce. Molecular gas, the cold, dense material that forms stars, can also be entrained in these outflows, swept up and accelerated away from the galaxy's center by the same radiation pressure and jet-driven mechanical energy. The consequences for star formation are significant. In the densest, most gas-rich mergers, the same systems where starburst activity is most intense, the black hole at the center is also most likely to be fed the largest supply of gas. Its feedback may eventually disperse or heat the same molecular gas that was fueling the starburst. The outflow carries that gas outward, reducing the supply available to collapse into new stars. In some systems, the signatures of this process are visible simultaneously. Young stars forming at extraordinary rates in one part of a galaxy, while a quasar-driven outflow races outward through the same galaxy at speeds that will eventually evacuate the remaining gas. Two processes running at the same time, one building and one clearing, the starburst spending down the gas reservoir while the active nucleus drives the remainder out. What remains after both processes have run their course is a galaxy changed at the deepest level. The two original spiral disks are gone. The orderly rotation that once defined each galaxy, the grand pattern of stars and gas moving together in a flattened plane, has been scrambled by the violence of the merger. The stars from both systems now move in orbits that fill three dimensions rather than a disk, their individual trajectories randomized by the complex and changing gravitational potential they traveled through during the collision. The combined system gradually settles into a new equilibrium, a smooth spheroidal distribution of stars whose surface brightness falls off in a characteristic way, with distance from the center the profile of an elliptical galaxy, one of the most common and most massive types of galaxy in the present-day universe. The active nucleus quiets as its gas supply diminishes, the outflows disperse and slow. The starburst, deprived of fresh molecular gas, fades. The post-starburst phase leaves its record in the spectrum of the light that comes from the galaxy, strong absorption lines from a large population of stars that formed during the burst and are now aging together, their more massive siblings already dead and gone, their intermediate mass members still shining with the warm glow of A-type stars before they too fade. This spectral signature marks a galaxy that was recently very active and is now growing still. In the outer regions of the merged galaxy, where the density of stars is lower and the crossing time for orbits is longer, the signatures of the merger persist even after the inner regions have relaxed. Shells, thin curved sheets of stars, can appear at large radii, formed by stars from the infalling galaxy whose orbits aligned along particular directions during the merger and have not yet had time to wind away. These shells are thin enough to be visible as ripples in the smooth light of the outer galaxy, arcs that do not follow the simple contours of an undisturbed elliptical. They are the last legible features of the spiral that was absorbed, its stars still remembering the direction they came from even after all other evidence of their original home has been erased. The merged supermassive black hole, now a single object, the mass of both progenitors combined, sits at the center of this quieted system. In the immediate aftermath of coalescence, general relativity predicts that the merger radiates not just gravitational waves, but also a net asymmetric kick, a recoil of the merged black hole due to the asymmetric emission of gravitational radiation during the final moments of inspiral and coalescence. The magnitude of this kick depends on the mass ratio and the spins of the two black holes, and in some configurations, models suggest it can reach thousands of kilometers per second. A kick of that scale might be enough to eject the merged black hole entirely from the host galaxy, leaving the galactic center empty for a time before a new cycle of accretion begins. More modest kicks may simply displace the black hole from the very center, setting it oscillating around the nucleus like a pendulum in a very deep well, losing energy to dynamical friction again until it settles back. The range of possible outcomes is wide, and each depends on parameters, the spin orientations of both black holes, the exact mass ratio, the configuration of gas and stars near the binary at the moment of coalescence, that are difficult or impossible to determine for any specific system from the outside. But across the full population of galaxy mergers in the universe, statistical patterns are beginning to emerge. The most massive galaxies in the present-day universe, the giant ellipticals at the centers of galaxy clusters, are believed to have grown to their present sizes through repeated mergers over cosmic history. Their central black holes, now among the largest known, some approaching tens of billions of solar masses, accumulated that mass through the same repeated process of merger and accretion, growing heavier with each coalescence. Some of the most extreme systems offer a direct window into what this process looks like in operation. At a distance of 3.5 billion light years, there is a blazar, a galaxy whose central nucleus launches a jet of relativistic material directly toward the Earth, making the nucleus itself visible at extraordinary apparent brightness across that vast distance. This system, cataloged as OJ 287, has been observed in optical light for more than a century, with historical plate archives extending its light curve deep into the past. The light curve shows a pattern, outbursts occurring roughly every 12 years, each one a rapid, dramatic brightening followed by a slower decay. The outbursts do not fit any simple model of a single active nucleus. They require, in the picture that has emerged from decades of theoretical work, a second black hole. The best current model places a secondary black hole of roughly 150 million solar masses in an elliptical orbit around the primary, which carries approximately 18 billion solar masses. The orbit is not circular. It precesses. Its long axis rotates slowly due to general relativistic effects, and the result is a complex evolving trajectory that brings the secondary through the plane of the primary's accretion disk, approximately twice in each 12-year orbital period. Each passage through the disk produces a flare. The secondary punches through the dense gas of the disk, drives a bubble of heated gas outward, and that bubble expands and cools and radiates a thermal pulse across a specific timescale. The timing of these outbursts, measured against the predictions of a general relativistic model of the binary's precessing orbit, provides a test of general relativity in a regime of strong gravitational fields and large masses that no other system currently accessible can match. The orbital period is 12 years. The precession of the orbit is measurable. The mass of the primary is constrained by the precession rate, because in general relativity, the rate of orbital precession depends on the masses involved and the orbital parameters in a precise, calculable way. The model predicts the next outburst timing, and the prediction has been tested against observation multiple times. The agreement between prediction and observation within the uncertainties supports the model, and the model requires a black hole of roughly 18 billion solar masses, one of the largest inferred from any current method, sitting at the heart of a galaxy 3.5 billion light years away, with a much smaller companion already on its way to eventual coalescence. What OJ 287 shows is that the binary stage, the phase theorists once worried might be permanent, stalled at a parsec, the two black holes circling each other indefinitely while waiting for a mechanism to carry them closer, is real and traversable and observable from the outside through the light curve of a system that has been, in a sense, recording its own orbital mechanics for over a century. The outbursts are the binary announcing itself in the only language available, ordinary light, produced by an extraordinary event repeated every 12 years, as reliably as any clock. The light from OJ 287 set out toward the Earth when the universe was just over 10 billion years old. It traveled across 3.5 billion light years of expanding space, through the diffuse intergalactic medium, past other galaxies and clusters and filaments, arriving finally at the detectors of optical telescopes in the present moment. Arriving finally at the detectors of optical telescopes in the present moment. Arriving finally at the detectors of optical telescopes in the present moment. Arriving finally at the detectors of optical telescopes in the present moment. carrying in its brightness variations the signature of two black holes in orbit around each other at separations that will, across some future time span measured in millions of years, continue to shrink. What the next stages of that in spiral will look like, whether the final parsec in that system will be crossed by gas inflow or stellar dynamics or some other mechanism, is not yet known. The binary is still far from coalescence. The signal it sends across its enormous distance is the signal of a process still underway, not concluded. The gravitational wave background that pulsar timing arrays are beginning to read is made of signals from systems like this one, and from systems far more extreme, from systems already merged, from systems at every stage, from first approach to final ring down, distributed across billions of light years and billions of years of cosmic time. Each contributing system was once two separate galaxies, each carrying its own central mass, falling together under gravity across the same long process that has been described here. The inspiral of their black holes was the final consequence of a collision that began when two dark matter halos first disturbed each other across a distance of hundreds of thousands of light years, that continued through tidal distortion and star formation and the collision of gas clouds and the gradual scrambling of stellar orbits, and that ended, insofar as it ended anywhere, in the merger of the two most massive objects that either galaxy contained. The universe holds billions of galaxies. A large fraction of those galaxies have undergone at least one significant merger in their history. Each merger carried a pair of central black holes through the stages described here. Dual activation, slow in spiral, the final parsec, and in time coalescence. All of those coalescences, spread across the history of the universe, produced gravitational waves. Those waves travel at the speed of light and do not significantly attenuate, and they have been accumulating in the fabric of space-time since the first galaxies merged in the early universe, billions of years ago. The background is old. Tonight's tale, it carries information about merger history at epochs when no other observation can reach directly into the dynamics of galactic cores. To hear it, even faintly, even as a statistical tendency in the correlation between pulsar timing residuals, is to receive a signal that has been traveling since the universe was young, from processes that were complete long before the solar system formed. The millisecond pulsars that serve as the receiving elements of this instrument were themselves created in stellar deaths, their rotation accelerated by mass transfer over timescales of hundreds of millions of years, their clocks set to a precision that dwarfs anything built by hand. They did not know they were being calibrated. They did not know they would one day serve as the elements of the largest gravitational wave detector ever used. They simply spun and ticked and sent their pulses out in all directions, and some of those pulses arrived at the Earth at moments when instruments were finally ready to receive them with the precision required. There is something very still in that picture. The pulsars are scattered across the galaxy. Each one is a dense dark remnant spinning hundreds of times per second in the silence between the stars, sending its signal outward without a destination, without a source of new energy, running on the momentum of a collapse that happened millions of years ago. The gravitational background they are listening to is also running on momentum, the orbital energy of black hole binaries slowly radiating away into the geometry of space itself, a process that produces no heat, no light visible to any ordinary detector, no chemical change in any surrounding medium. It is a transaction between mass and space-time, carried out in a frequency range so low that cycles of oscillation span years and decades, perceptible only across baselines as wide as the galaxy, only across observation windows measured in years. And yet the signal is there. In the data, carefully measured and carefully analyzed, the Hellings Downs correlation appears. The shape of space through which the pulsar signals travel has been very slightly, very regularly, very measurably disturbed by the gravitational radiation of merging black holes across the observable universe. The first evidence of this disturbance is not loud. It is quiet, statistical, the kind of finding that accumulates slowly from years of observations and reveals itself not in any single moment, but in the gradual convergence of a correlation function toward a theoretical prediction. The era of greatest galaxy merging has already passed. The rate of major mergers was highest when the universe was younger and denser, when galaxies were closer together and moving through a space that had not yet been stretched as far by its own expansion. The mergers that are happening now, and they are still happening in the present epoch, though less frequently than in that earlier time, are the survivors of that original era. The systems whose orbital parameters and approach velocities happen to bring them together at these late times rather than earlier ones. The gravitational wave background contains contributions from all of those epochs, from early mergers and late ones, each contributing a piece of the accumulated signal. What remains, in the quiet that follows each completed merger, is an elliptical galaxy with a single massive center, its star formation diminished or extinguished, its spiral structure dissolved, its merger history encoded in the chemistry of its stars and the subtle shapes of its outer light. The black hole at its center is the heaviest thing the system contains, grown large by the same chain of events that made the galaxy itself grow large. It sits in the silence at the center of a system, still slowly cooling, still losing the energy that the merger injected into its stellar orbits, still settling toward a quieter equilibrium that it will approach but never fully reach before another galaxy, another dark matter halo, another accumulation of stars and gas, draws close enough to begin the process again. The collapsed remnant turns slowly in the dark at the heart of a system too old and too quiet to be mistaken for anything young. No spiral arms sweep outward from it. No disk of cold gas traces the plane of a rotation it no longer has. The light that falls from it is the light of old stars, red and cool and steady, the light of a stellar population that formed long ago and has been aging undisturbed ever since. At the very center, invisible to every instrument except the orbits of stars passing close enough to feel its gravity, the merged black hole waits in the way that objects with no need of patience wait, without expectation, without awareness, simply present and massive and deep and still. In the present sky, on a clear and moonless night, far from any city, the Andromeda Galaxy is already there. It does not announce itself. It sits just off the shoulder of its constellation, a faint oval smudge of cold light, smaller in apparent brightness than the surrounding stars, and yet larger in true extent than anything else visible to the naked eye. What the eye catches is only the dense bright core. The full disk, stretched wide with its spiral arms and its attendant clouds of gas, spans a width across the sky more than 6 times the width of the full moon. Most of that is too faint to see without instruments, but the center is there, a soft, diffuse glow, calm and unmoving, as it has been every clear night for as long as there have been human eyes to notice it. It is falling toward us at 110 kilometers per second. That is the velocity along the line of sight, measured in the light it sends, each wavelength compressed slightly toward the blue end of the spectrum by the diminishing distance between that galaxy and this one. 110 kilometers per second sounds fast, It is not fast, not by the measure of what needs to be crossed. The distance between the Milky Way and Andromeda is 2.5 million light years, a span so deep that the light now arriving from that faint smudge set out before the earliest stone tools, before the genus we belong to existed, before the great grasslands of Africa had taken their present shape. At 110 kilometers per second, crossing that distance takes longer than the current age of many mountain ranges. The approach is real, the closing is certain, but it is the slowest certainty in the life of anything alive today. This is not a danger drawing near. It is a deep time event already in progress, already decided, already sealed into the orbital mechanics of two massive systems that have been bound to each other since the universe was young and the local group of galaxies was still contracting out of the early cosmic web. The fate is written in the numbers. The collision is not a possibility, but a schedule, patient and absolute, unfolding across a span of time no living thing will witness, whole. The measurement that confirmed the course came from long observation. Over several years, the Hubble Space Telescope tracked the positions of faint background quasars seen through Andromeda's disk, using those distant fixed points as a reference against which the galaxy's drift across the sky could be measured. The motion was tiny, a shift so small that expressing it in any unit familiar to ordinary experience makes it seem stationary, but the measurement was made with enough precision to answer the most important question. Was Andromeda passing across the sky in a direction that would carry it wide of the Milky Way, a near miss that would distort both galaxies and leave them moving apart again, or was its path almost directly inward, aimed for something close to a head-on approach? The answer, published in 2012 by a team led by the astronomer Roeland van der Merel, was the second. The transverse velocity, the sideways motion, the part that would carry it wide, was small, not zero, but small enough that the two galaxies will not simply brush past each other. They are aimed within the tolerances of the measurement for a collision. The word collision is worth sitting with for a moment because it carries associations that the event does not deserve. Two galaxies colliding are not two solid objects striking each other. A galaxy is almost entirely empty space. The stars within it are separated from one another by distances so vast that even in the densest galactic center, the average distance between stars is measured in fractions of a light year, and a light year is nearly 6 trillion miles of empty space. When two galaxies pass through each other, the stars within them almost never touch. They do not even come meaningfully close. The probability of any individual star in the Milky Way directly striking any individual star in Andromeda throughout the entire duration of the merger is vanishingly small. What collides is not the stars. What collides is the gravity, the immense invisible field that each galaxy generates, which reaches far beyond any visible disk of stars and extends in the dark matter halos surrounding each galaxy for hundreds of thousands of light years in every direction. Those halos are already touching. They are already interacting. The merger in the deepest technical sense has already begun. Gravity does not wait for visible material to meet. Long before any luminous disk comes close to another, the dark matter halos surrounding each galaxy have begun to feel one another's pull. The halos are vast, diffuse, structureless, not made of ordinary matter, and emitting no light, but real in their gravitational effect, which is the only sense in which anything in the universe is finally real. As the halos overlap and interpenetrate, dynamical friction begins to drain the orbital energy of the two approaching systems. Each galaxy loses a little speed. The loss is small at first, and the distance is still immense. But the trend is set, and over the span of billions of years, what was a slow approach will become a fall. The first close passage of the two bright galactic disks is predicted to occur in roughly 4.5 billion years. On the scale of cosmic time, that is not very far away. The sun will still be burning, though it will have grown somewhat brighter and hotter by then, and the inner planets will be correspondingly warmer. Life on Earth, if anything persists that long, will be different in every possible way from anything alive today, shaped by 4 billion more years of evolution, extinction, and change that no forecast can sketch. But the stars themselves, including the sun, will still be there, still moving, still orbiting within a galaxy that will by then be a very different place. In the sky of that distant future, Andromeda will no longer be a faint smudge. In the long approach over billions of years, its angular size in the sky will grow. Roughly a billion years before the first close passage, it will be large enough to show its spiral structure to careful observation. 500 million years before, it will span a noticeable arc, and in the last hundreds of millions of years before closest approach, its disk will be enormous, spanning many times the width of the full moon, its spiral arms and dust lanes, and the soft glow of its stellar population filling a great arc across the night sky. The most impressive single sight in any clear night for any observer alive at that time. The Milky Way's own band, the glow of the disk seen from inside, will still stretch across the sky, but competing with it now will be the vast luminous presence of another galaxy, close enough to resolve, close enough to watch the outer fringes of its stars beginning to distort under the first tidal forces of the approach. The first pericentric passage is not the end, it is not even close to the end. In simulations of this merger, built using the best current measurements of the masses, velocities, and internal structures of both galaxies, the first close pass sends the two systems swinging past each other, and then, under the pull of their mutual gravity, drawing back. They are bound. Whatever the geometry of the first pass, the total orbital energy of the system is negative, which in the language of orbital mechanics means there is no escape. The two galaxies will approach, swing past, separate to some lesser distance, and then fall back again. Each pass dissipates a little more orbital energy. The separation after each close approach is smaller than the separation after the last. The spiral inward is gradual, a long series of approaches growing progressively tighter until the two nuclei, the dense central regions of each galaxy, each containing a supermassive black hole, draw close enough that their combined gravitational interaction begins to mix the stars of both systems irreversibly. By roughly 6 to 7 billion years from now, the two galaxies will have merged into a single object. The merged remnant will not look like either of its parents. The Milky Way is a barred spiral, a flattened disk with arms winding outward, and a dense central bar of stars, shaped by angular momentum and gas dynamics into the orderly, rotating structure that has characterized it for billions of years. Andromeda is also a spiral, larger and more massive, with its own disk and arms and central structure. Spirals form and maintain their shapes because of the ordered rotation of the stars and gas within them, material moving on nearly circular orbits in a common plane, gravity and rotation in a balance that produces the graceful pinwheel form. When two spirals collide, that ordered rotation is destroyed. The stars, flung onto new orbits by the tidal forces of the collision, no longer move in the same plane or in the same direction. Their orbits become elongated, tilted at every angle to one another, randomized by the gravitational chaos of the merger. What emerges after billions of years of phase mixing is not a disk. It is a sphere, or close to one, a smooth, diffuse, roughly oval distribution of stars, in which the history of two separate rotating disks has been erased by the violence and the time of their collision. The merged object will resemble a large elliptical galaxy, or something close to a lenticular, a smooth oval of stars, with no prominent disk, no spiral arms, no great sweep of structure. Astronomers who study this merger have given the future remnant an informal name, Milkomeda, or sometimes Milkdromeda, a compound of the two names, gentle and a little absurd, acknowledging that this distant object will carry within its stellar population the stars of both its progenitors, thoroughly mixed and no longer distinguishable from one another by position or orbit. The distinction between Milky Way and Andromeda stars will survive in principle, encoded in the chemical compositions of the stars formed before the merger, but the structure that organized those stars, the two spirals, the two disks, the two sets of arms, will be gone. The solar system, in all of this, is not destroyed. It is not disrupted. The sun and its planets will continue to orbit within the gravitational structure of the merged galaxy, as they have always orbited within the gravitational structure of the Milky Way. Stars do not strike each other during the merger. The solar system's internal structure, the sun, the planets, their moons, and their small bodies, is bound together by local gravity, far too strong to be disturbed by the slow, large-scale gravitational changes of a galactic merger happening over billions of years. Whatever happens to the Milky Way as a whole, the Earth will remain in orbit around the Sun, the Moon will remain in orbit around the Earth, and the small, warm, rocky world at the center of this system will persist through the entire merger, changing in other ways, driven by other processes, but not disrupted by the collision itself. What may change in the simulations is where within the merged galaxy the solar system ends up. Today the Sun orbits at a moderate distance from the galactic center, on a nearly circular path that has carried it around the galaxy dozens of times since it formed. During the merger, the gravitational disturbances of two interacting systems, the tidal forces, the redistribution of mass, the shift in the overall gravitational potential as the two galaxies interpenetrate and reorganize, will perturb the solar system's orbit. Some simulations find a significant probability, estimated near 50% in several models, that the solar system will be scattered to a considerably larger orbital radius within the merged remnant, moved outward from what was the galactic center into the more diffuse outer regions of Milkomeda. Whether the solar system ends up closer in or farther out, whether it finds itself in a dense central region or drifting in the quiet outskirts, depends on the specifics of each close passage and on small differences in initial conditions that accumulate over the billions of years of the merger. The outcome is not known with certainty. The probabilities are estimates built from simulations that cannot track every star and every gravitational perturbation with perfect precision. What the simulations do agree on is that the Sun and Earth will survive, and that the night sky will be transformed. In the early stages of the merger, the sky will grow spectacular in a way that no life today could witness. During the first close passage, when the two galactic disks sweep past each other at close range, the night sky will be lit by the presence of another galaxy at near range, its stars spread across a vast arc, its gas clouds and stellar streams visible as structure, its gravitational distortion of the Milky Way's own disk producing warps and distortions in the familiar band of the galaxy. The rate of star formation will spike as compressed gas collapses across large regions of both galaxies simultaneously, and the sky will hold more bright, young, hot stars than it does today, blue and luminous and burning fast. The interstellar medium of both galaxies will be churned and disturbed, gas flowing and compressing and shocking along the collision front, and the general appearance of the sky from any surface will shift in ways too slow to watch directly, but too large to miss across millions of years. Later, as the two nuclei draw together and the merged remnant begins to take shape, the sky will change again in a quieter direction. The star formation triggered by the merger will exhaust much of the available gas. The brilliant young stars will burn through their short lives and die, leaving behind their heavier descendants or their compact remnants. The galaxy that forms from the merger will be, in the long run, older and redder, its stellar population weighted toward the long-lived lower mass stars that the merger's starburst did not have time to form in great numbers, but that were already there in both progenitor galaxies, quietly aging. Elliptical galaxies, which Milkometa will closely resemble, tend to be red and relatively quiet, not because their stars are gone, but because the raw material for new star formation has been consumed or dispersed, and what remains is the light of stars that formed long ago and are still slowly burning down. From any surface within Milkometa, the Milky Way band will be gone. This is one of the stranger things to hold, that the long, soft river of light that stretches across the sky on dark nights, the sight that has oriented every human culture that has ever looked up, is a feature of living inside a disk galaxy. It exists because the stars of the Milky Way are gathered into a flat structure, and when a viewer inside that structure looks outward along its plane, the density of stars piles up into a visible strip of light. An observer inside an elliptical galaxy does not see this. The stars in an elliptical are distributed in all directions without a preferred plane, and the night sky from inside such a galaxy holds stars spread more or less uniformly in every direction. No bright band, no dark rift where dust clouds absorb the distant light, no concentrated glow across the zenith. The night sky will be more uniformly populated with stars, but without the river of the Milky Way, a whole dimension of the sky that every living thing on Earth has shared for the entire history of life. The long stripe of the galaxy, the foundation of every constellation map and every mythological sky, will no longer exist. The two supermassive black holes at the centers of the Milky Way and Andromeda will, over the course of the merger, also draw together. Each galaxy's central black hole will sink toward the center of the merged remnant, losing energy through interaction with surrounding stars, approaching the other over millions and then hundreds of millions of years. The path is slow. The separation decreases with agonizing gradualness, and at some point the two black holes will form a gravitationally bound binary, two immense masses orbiting each other at a separation that by galactic standards is nearly nothing, perhaps a parsec or less, a few light years at most. From that binary orbit, they will eventually merge, the final approach driven by the emission of gravitational waves, ripples in the fabric of space-time, spreading outward from the orbiting pair at the speed of light, carrying energy away from the system, and drawing the two masses closer with each orbit, until in a final fraction of a second they become one. The gravitational wave signal from that final merger will be brief and powerful, a chirp in the curvature of space-time audible, in principle to instruments sensitive to the right frequencies, instruments far more capable than anything built today, but instruments of a kind that future beings might build, if future beings exist. The merged black hole will settle into its new configuration, radiating the last asymmetries away as further gravitational waves, and then it will be still. Gaia, the European Space Agency's astrometric observatory, has been extending and refining the measurements that first fixed Andromeda's trajectory. Its observations, combined with continued Hubble monitoring, are building a more complete picture of not just the two main galaxies, but their attendant satellites as well. The Triangulum Galaxy, M33, the various smaller companions that orbit both systems, each carrying its own momentum and its own role in the gravitational future of the local group. The picture that is emerging is not of two isolated galaxies on a simple two-body collision course, but of an entire group of gravitationally entangled systems, all falling slowly toward a common future in which the larger members will eventually absorb the smaller ones, and the local group will gradually consolidate into a single large remnant galaxy surrounded by a dispersed halo of stars and smaller companions. On timescales of tens to hundreds of billions of years, even the outlying members of the local group are expected to merge with the central remnant. The final object will be something very large and very old and very quiet, embedded in a universe that has expanded so far and cooled so much that new galaxies are no longer forming, and the nearest other galaxy grouping is moving away too fast for its light to ever arrive. That is the far end of the story, too distant even for the scales that apply to Andromeda's approach. The merger of the Milky Way and Andromeda is an early chapter in that long closing, not the final one. It is the beginning of the consolidation, the first major step in the eventual gathering of this corner of the universe into a single aging system. For now, the faint smudge in the constellation it shares with a princess of old stories is there on clear nights, unchanged in any single human lifetime, unchanged in any 10 human lifetimes, appearing to move across the sky with the daily rotation of the Earth and the annual circuit of the seasons, exactly as every other star and galaxy appears to move, giving no outward sign that it is falling. The light arriving tonight left that galaxy 2.5 million years ago, carrying no information about anything that has happened in the universe since then, traveling at the only speed available to it, crossing the void without slowing, without spreading, arriving here at a particular patch of sky where a planet circles a star in the outer part of one of the two galaxies destined to meet. The closing is certain. The course is set. The two systems have been falling toward each other across the whole span of time that separates the earliest stone tools from today, and they will continue falling across a span many times longer than that before the first close approach. There is no force that will interrupt this. There is no contingency. The physics that govern it, gravity, the conservation of orbital energy, the behavior of dark matter halos as they interpenetrate, are settled and stable, and the outcome they predict is not in doubt in its broad shape, only in its precise details. Somewhere in the faint oval of light, visible on dark, clear nights, stars are going about their slow lives, each one following its own orbit around a galaxy that does not yet know it is falling. Some of those stars may have worlds around them. Some of those worlds may have surfaces